A buffer is a solution that is able to resist changes in pH, which means if you add in acid or you add in base, then the buffer is going to try and neutralize that acid or base addition and keep that pH more constant. So before we get too far into discussing buffers, I want us to discuss something called the common ion effect. What is the common ion effect? Well, it's a shift in equilibrium due to the addition of an ion that's already involved in the equilibrium expression. Now, what in the world do I mean by that? I mean, let's pretend we have a solution that is composed maybe of something like hydrofluoric acid. So if we have hydrofluoric acid, we know that we've got an equilibrium that's going to be established by this reaction, where your hydrofluoric acid is a weak acid, so it dissociates, but only partially, into hydrogen and fluorine. If we add something like sodium fluoride to that mix, we are going to produce sodium ions and fluorine ions. And notice we have a single arrow, and that's because your sodium fluoride is going to completely dissociate. Well, we already have an equilibrium reaction that's going to be set up with hydrofluoric acid. If we add in that sodium fluoride, we have something called the common ion, which is just like what it says. You're adding in a salt that has an ion that's already involved in an equilibrium reaction going on in solution. And so you would see stuff shift just like you would expect from Le Chatelier's principle. And so equilibriums shift to adjust that change. So what does this have to do with buffers? Well, buffers do that. They have a weak acid and its conjugate base, or a weak base and its conjugate acid. And so it's going to adjust because of the same idea beyond a common ion effect. And so to kind of lead into and explain it, we're going to work some common ion problems, pretending that it's not a buffer, but then look and see how it's similar to a buffer in that respect. So the first problem that I want us to look at is one of a 1 molar solution of hydrofluoric acid. And I want to know, what is the pH? Now, you've probably already done enough weak acid problems by now to note that if you have a 1 molar solution of hydrofluoric acid, you're going to end up calculating your equilibrium Ka is going to be equal to x squared over your initial concentration minus x. But I want us to go through the whole process of creating the ice table, figuring out what those equilibrium species is before we solve for the problem. You do know enough, I'm sure, to know that you cannot take pH as negative log of 1 molar, because that's only true for a strong acid problem, and hydrofluoric acid is a weak acid. So we have hydrofluoric acid, which is dissociating into hydrogen ions and fluorine ions. Initially, we have 1 molar of hydrofluoric, no hydrogen, and no fluorine. My change then is going to be dependent upon the fact that my products, I don't start out with either of them. And so those have to increase because they can't decrease, and we're going to decrease my hydrofluoric. And so I end up with 1 minus x, x, and x, which means my Ka, which is in this case equal to 7.2 times 10 to the minus 4, and that's just the Ka that you could look up in a table for hydrofluoric acid. And I know that my Ka is going to be equal to my equilibrium expression, which in this case is hydrogen ions times my fluorine ions all over my hydrofluoric acid. So if that's a true statement, which it is, then we're able to write 7.2 times 10 to the negative 4 equals x squared over 1.0 minus x. And we can assume that this x goes to 0 because 1 is at least 100 times greater than Ka. Then I can solve for x, and so x equals 2.68 times 10 to the negative 2. Now it's important to remind yourself at this point, what does x stand for? X stands for hydrogen ion concentrations. So because of that, we can say pH equals negative log of my hydrogen ion concentration. Therefore, pH equals negative log of 2.68 times 10 to the negative 2, or my pH, plug that into your calculator, equals 1.57. And so there's my pH for this solution. But I thought we wanted to look at examples of the common ion effect. So how about we take that same hydrofluoric acid and add in another compound that has a common ion, like the sodium fluoride we discussed earlier. So for this problem, we're going to have a 1 molar hydrofluoric solution that is also 1 molar in respect to sodium fluoride, and we're asked the same question of what is the pH. So for this case, we need to remind ourselves that sodium fluoride is going to completely dissociate into sodium and fluorine ions. So if you start out with 1 molar of sodium fluoride, it's going to go to 0, and each of your products is also going to now turn into 1 molar solution. So I can go back to my ice table that I set up, and we need to figure out how does that affect equilibrium. And so in this case, we've got our initial concentration, which remains the same, but we have a new common ion. And so my hydrofluoric is 1 molar. And so I can plug that in here into my ice table for my fluorine concentration. And so I'm starting out with 1 molar of that. Now the same thing as before, I don't have any hydrogen ions. And so what that means is my equilibrium must shift to the right to create hydrogen, which would also similarly create fluorine, but it would take away from my HF. And so here I have 1 minus X, 1 plus X. I can plug all that now into my equilibrium expression, and I end up with X times 1 plus X all over 1 minus X. Now before I had made the assumption that my X could go to 0 as a denominator, I still can do that. But on the top, my numerator here can actually go to 0 as well. Why? Well, the reason your X can go to 0 is because we're assuming X is really small compared to my initial concentration, which it was. If the same is true here, 1 minus X should be approximately 1. And if that's true, 1 plus X should also be approximately 1. So it might be 1.00001 and 0.99999, but they're both going to be approximately 1. So this translates to X equals 7.2 times 10 to the negative 4 approximately, which means our pH, because X once again is equal to our hydrogen ion concentration, the pH equals negative log of 7.2 times 10 to the negative 4, or pH equals 3.14. And so we can see it's a much different pH when we added in a common ion. Something else to note is that, remember, sodium fluoride, sodium is a neutral species, fluorine is basic, it's a basic salt. And so because of that, we expect the shift to become more basic, which it did, because 3.14 is higher, therefore it's more basic than my 1.57 pH. And so these are all little things to kind of remind yourself that you expect this as kind of a common sense check. All right, but let's go back up here to Le Chatelier's principle. The common ion effect. We expected a shift in equilibrium due to the addition of an ion already involved in the equilibrium expression. So wouldn't we expect that if we add in fluorine, we expect equilibrium to shift to the left compared to our part A? And that's the important part, because in this case, our X is a whole lot smaller. Look at this values. X here is 10 to the negative 2, whereas this X is 10 to the negative 4. You better believe it shifted left. There is less hydrogen being created than was originally. And so that's how Le Chatelier's principle plays into that. Is this X down here for part B is a lot smaller because compared to part A, it shifted and created more of the reactant. All right, so how does this apply to buffers? Well, a buffer is simply a weak acid and its conjugate. I'm going to write this down. Weak acid plus its conjugate base, or the opposite of a weak base plus its conjugate acid. And so if that's true, that is exactly what we saw up here, where hydrofluoric acid is our weak acid and its conjugate is fluorine, and that is our conjugate base. And so here, by adding in a common ion, you're essentially satisfying the rule for a buffer. So kind of the second part of this video is, can we go from the ideas of using a Ka and a weak acid problem to a buffer? And is there an equation that relates us to a buffer? And There absolutely is. So let's look at that algebra now. What you see at the top for this is our equilibrium expression. Down here at the bottom is our buffer equation. In this video, we're going to attempt to go from one to the other just using algebra. Now, this equation that you see down here is our Henderson-Hasselbalch equation. I call it HH for short, or you can also call it the buffer equation. So how do we do this? How do we go from this to the next one algebraically? Well, first you multiply both sides of the expression by your HA over A minus, because that's going to allow these two to cancel, leaving us with this next equation. And then we take negative log of both sides to go to the next equation. And then algebraically, we can just simply say, all right, if negative log of HA over A, it's also times K, you can simply write that as two log expressions. Algebraically, it's the same. But then how do I go from this equation to this equation? What's different? Well, the rules for logs are if you invert the numerator and the denominator for what's inside the log, you simply change the sign. And so that's what's happening in this is we flipped the numerator and the denominator, which changes the sign of the log. And then the last step is we replace this negative log with the letter P. P literally means negative log. So instead of saying negative log of hydrogen ion concentration, you can simply say pH. And instead of negative log of Ka, you can say pKa. And so here you can see the final expression for the Henderson-Hasselbalch equation. I also like to write it sometimes as pH equals pKa plus the log of my base over my acid. I do that sometimes just to kind of remind myself the more basic species on top, the acid is on the bottom. There's one more important piece of the puzzle though, and that is your Ka goes with the HA. So whatever your acid is, you must use the Ka that is associated with that acid. As long as you do that, you can utilize this equation. So could we have used it for our common ion expression up here? Absolutely. So let's try and use the buffer equation for this common ion problem. And so what we have here is our pH equals pKa plus the log of my base, which in this case is fluorine, over my acid, which is hydrofluoric acid. So we've got pH equals negative log of my Ka, the same Ka I used before, 7.2 times 10 to the negative 4, plus the log of my fluorine ion concentration is 1 molar, over my hydrofluoric acid concentration, which is also 1 molar. And I end up with a final pH exactly equal to what we had before of 3.14. And so either the ICE table or the Henderson-Hasselbalch would have helped us and enabled us to solve this common ion problem. And so in class, we're going to talk more about buffers, more about common ions, and just kind of think through all the principles that are involved in buffer problems.